All right, this is a little bit of a tricky question, so let's work through it together. It says that we have two fat pipes directly attached to the bottom of a water tank. I have my water tank. I have two fat pipes directly attached to the bottom. And it says that one of them is pinched off to make a nozzle. So I pinched off that one to make a nozzle. The other one is left wide open. We want to know how high up does the water squirt for both cases. Well, if I look at this problem, I can use Bernoulli's equation, which says P1 plus rho GH1 plus 1/2 rho V squared 1 is equal to P1 plus rho GH2, sorry, this should be 2's, plus 1/2 rho V2 squared. It just says that the pressure plus, or the static pressure plus the height change plus the dynamic pressure is constant. So if I look at both of these cases, they both have the same height change. So my height change from the top, I'm going to call this H1, this will be H2, and this could be H3. Well, we'll see that if we go down the same height, this is H1, it's going to start up here. H2 and H3, I'm going to set to be equal to 0. And set the bottom to be equal to 0. So that means that H2 and H3 both cancel out. They're both open. All of these cases I'm going to say are open. So P1, P2, and P3 are all going to be the same value. So P1 is equal to P2, which is equal to P3. So that just means that my height change plus my velocity for this one is going to give me my second velocity. Which means that both of these cases, since H2 can be replaced for, or P2 can be, sorry, my 2's can be replaced by 3's, that means my velocity 2, my velocity 3 have to be equal to each other. So any of them that are different are going to be not the correct answer. So above the water level of the tank for the pinch pipe, below for the other one, equally high, that's one that's still available, up to the water level for both tanks, and higher for the pinched pipe but less high. So I'm down to two answers. They both are going to go to the same height because they have the same velocity. Same water with the same velocity, or any object with the same velocity and the same gravity is going to go to the same height. So the question is, how high does it go? Well, I'm going to make one simple assumption here, and I'm going to say that the velocity of the tank is going to be negligible. So I have rho GH1 is equal to 1/2 rho V2 squared. V2 or V3, they're the same value. Well, this just gives me that G and the rho and the rho cancel out, so I get that the height that this thing goes, or I can rearrange this equation, and I see that this height can be rewritten as 1/2 V squared over G. So the height that we start with is going to be equal to the velocity that it eventually becomes when it goes through either of the pipes, divided by G with a 1/2, and make sure we're square things. Well, if I were to look at a different equation, so this equation is using Bernoulli's equation, just rearranging it. If I were to actually look at the kinetic energy, again, saying that this height right here is my potential energy equaling 0, I'm going to get that my K plus U initial is equal to K final plus U final. And this is for, my initials are going to be where it starts, and I'm going to figure out my final heights where it ends. So it starts off with 1/2 mv2 squared plus 0 height is equal to 0 final velocity, how high it goes to 0 velocity, plus mgh final. I'll notice that my masses cancel, and I get the 1/2 v2 squared over g is equal to my h final. So my h1 is eventually going to be the same as my h final, which means that this water is going to go up to the same height as the tank itself. It's going to stop there. So the water it'll go up to the water level of the tank for both systems. So I use Bernoulli's equation to figure out a relationship between its initial height and its velocity, and then I use conservation of energy to figure out the final height based off of an initial velocity. And we found that the initial height that the water level starts with is going to be the same as the height of the water that it flows up to. Kind of a cool little result, but kind of makes sense in terms of energy. If the water starts here and it goes down through some potential energy and then it goes back up the other side of a hill, it's going to go up to the same height.